Welcome back. This will be a video lecture on section 2.4 of the text. This is some applications. We're going to do two applications. There are many applications in this section, but we'll pick two. We're going to do an application to network analysis, and we'll do an application to finite linear games. Let's begin with our application to network analysis. Now, before we study this problem in earnest, let's take a look at this picture below here. So this is a picture of a network. Now this network could be describing lots of different things, but let's fix our minds on this model. Let's think of this as a flow of water through pipes. So the pipes are being indicated by these directed arrows. So this arrow is telling me that water is flowing into node 1, and the number on the arrow is telling me, let's say, the number of gallons per minute. So there's 20 gallons of water per minute flowing into node 1. This arrow is telling me that out of node 1, we've got some unspecified amount of flow going from node 1 to node 3 along this pipe, and another unspecified amount of water flowing from node 1 into node 2 along this pipe. Okay, so we understand that the directed arrows are pipes. They're telling us the direction of flow, and the numbers attached to those pipes are telling us how many gallons per minute are flowing along that pipe into these various nodes. All right, now one thing I want you to notice is that coming into this system of nodes, we've got a total of 50 gallons of water per minute, and exiting this system, we have another 50 gallons of water per minute. Now we're going to assume that this system is conserving all of the water, right? That at each and every one of these nodes, the water is neither being created nor destroyed. All right, the water is simply passing through. So all the water is being conserved, so that at each and every node, the amount of water flowing into the node has to equal the amount of water flowing out of the node. So we're assuming the conservation of water principle at each and every one of these nodes. Okay, let's take a look at the two parts of this problem. So part 1 asks us to describe the set of feasible values for the flows F1, F2, F3, and F4. All right, we'll go to the document camera in just a bit, and I'll show you how to set that up as a system of equations. Part 2 says if F3 is at its maximum, so if the flow along this pipe is at its maximum, what are the values of F1, F2, and F4? Okay, so let's head over to the document camera. I'll show you how to use this conservation principle to write an equation at each and every node. We'll set it up as a system of equations, which we can solve very easily through row reduction, and I'll show you how we can describe the solutions to parts 1 and parts 2. All right, join me there. Welcome to the document camera. We've got our network pictured here, and all we're going to do is use our conservation principle. At each and every node, we're going to keep track of the inflow and the outflow, and we're going to set those equal to each other. That's going to give us a system of 4 equations in these 4 unknowns. So let's take a look at node 1. I'll keep the inflow on one side and the outflow on the other side, just so we can kind of keep track of things. So in node 1, I've got 20 units in, and that has to be equal to the F1 plus F2 units coming out. Okay, at node 2, I've got 20 and F2 units coming in, and that has to equal the F4 units coming out. All right, at node 3, I've got 10 and F1 coming in, and F3 flowing out. And then finally at node 4, I've got the F3 and F4 coming in, and that has to be equal to the 50 units coming out. All right, now what I want to do is rewrite these equations with, let's say, the unknown F's, 1 through F4 on the left and all of the constants on the right. So what are we going to see? We're going to see something like this. We'll have, for instance, this first equation could be written as F1 plus F2. I'm going to leave some space here, equals 20. Okay? Our second equation could be written as f2 minus f4 equals a negative 20. Okay, f2 minus f4 equals a negative 20. Our third equation would look like f1 minus f3 is equal to negative 10. And our last equation is already in a nice form. I'll just write it as f3 plus f4 is equal to 50. Okay, so there's our system of equations in the values f1 through f4. Now this immediately can be pulled and placed into an augmented system. And we can write that as 1, 1, 0, 0, 20, and 0, 1, 0, negative 1, negative 20, and then we'll have 1, 0, negative 1, 0, and that'll be negative 10, and then finally 0, 0, 1, 1, 50. Okay, so now this system has now been put into this augmented form. Now, I won't go through the details with you. You can row reduce this on your own or use some technology to help you. But you can go through a sequence of row steps. Right, so there's going to be a sequence of elementary row operations that you can go through. We're more interested in what the reduced row echelon form looks like. And so this is going to look like this. It's going to be 1, 0, 0, 1, 40, 0, 1, 0, negative 1, negative 20, 0, 0, 1, 1, 50, and then there's a row of zeros at the bottom. So we're going to see that there's going to be an infinite number of solutions to this system, right? So our variables are f1, f2, f3, and f4, and our leading ones are f1, f2, and or correspond to f1, f2, and f3. And so we can see that one interpretation of this is that f4 is a free variable, and so it's not going to have a fixed specified value. So let's set f4 equal to some parameter s, and let's work out the relationships between f1, f2, and f3 to that free variable. So this first equation is telling me that f1 plus f4 is equal to 40. So that says f1 is going to be the same as 40 minus s. This equation says f2 minus f4 equals negative 20. And so f2 is going to be s minus 20. This third equation says f3 plus f4 equals 50. So f3 is going to be 50 minus s. And of course, f4 is equal to s. Okay, now, as a mathematical solution, that's complete. S could be anything, and this would give us a complete solution. But there is actually one more constraint on this system, just due to the fact that this is kind of a natural system, and that's that all of these flows actually have to be non-negative. So there is one extra constraint here that's not, it's not coming from the mathematics, but it's coming from the physical constraint in the system, and that's that all of these flows have to be bigger than or equal to 0. Now, I can show you what effect that's going to have. We just have to look at each one of these and set it bigger than or equal to 0, and that's going to put some additional constraints on the range of possible values for s. So this first equation, we know that f1 has to be bigger than or equal to 0, so this says that 40 minus s is greater than or equal to 0, and that says that s has to be less than or equal to 40. So it's not possible to have the free variable s bigger than 40 because it'll make f1 negative. All right. We also have the constraint that s minus 20 is bigger than or equal to 0, and that says that s has to be at least 20. Otherwise, this one's negative. This constraint is saying 50 minus s must be bigger than or equal to 0, and that says that s has to be less than or equal to 50. but that's already superseded by this constraint that s is less than or equal to 40. So this is actually not giving me anything new. And then there's one more constraint, and that's that s itself has to be bigger than or equal to 0. But we already know that s has to be bigger than or equal to 20, so this one is actually not giving me anything new. So in fact, what we find is that the value of s, this free variable, in order to make this system physically meaningful, not mathematically meaningful, but physically meaningful, that value of s has to land between 20 and 40. Okay, so in order to make this flow mean something in nature, let's say, we have to make sure that our free variable is chosen somewhere between 20 and 40. Now, just as an example, let's just work out a case just so we know what's going on here. Let's imagine I set s equal to 30, which falls right in the middle of our range of acceptable values for s. That's going to set our flows at, let's see, f1 is going to come out to be equal to 10. f2 is going to come out to be equal to 10. f3 will be equal to 20. And f4 will be equal to 30. Okay, so if we go up to our picture here, that's going to put 10 here for f1. It's going to put 10 at f2. It's going to put 20 at f3. And it's going to put 30 at f4. So our system would look like this if we chose that free variable s to be equal to 30. And we can see that that actually works nicely, right? The 20 come in and we have the 20 leaving in this manner. We've got 30 coming in and 30 leaving, 20 coming in and 20 leaving, 50 coming in and 50 leaving. So that actually works nicely. Now, if we remember part B of this question, part B was asking us to think about the situation, right, where where F3, right, was at its maximum possible flow, right? Now, when we look at F3, we have to ask ourselves, what's the largest possible value for F3? Right now, it's 50 minus, we're seeing it as 50 minus S, but we know that S can range between 20 and 30. So our largest possible value for F3 is going to occur when S is at its lowest possible value. I mean, we're subtracting as little as possible. So the largest value for F3 is going to be 50 minus 20, or 30. And that's going to occur when S is equal to 20. So F3 is maximized at S equals 20. And that's going to give us the following choice of flows. When S is equal to 20, we're going to get a flow of 20 through F1, a flow of 0 through F2, a flow of 30 through F3, and that's as much as we could get through F3 under this consideration. And then F4 is going to be equal to S, which is equal to 20. All right, so that's an arrangement of flows that will put as much as possible coming through this pipe here. We can get this pipe up to as much as 30 by getting the flows arranged in this fashion. Okay, so hopefully you see that that's really it just reduces down to solving a system of equations, but we're using this conservation principle to kind of get the ball rolling. All right, we're going to take a look at one more type of application. Our next application is to what are called finite linear games. So in this problem, a set of 5 bulbs and 5 corresponding button switches A through E are shown below. So in this picture, the bulbs are represented by these open discs, okay? And each bulb has a switch located next to it. And I've got everything labeled A through E so we can kind of keep track of things. So this is a switch A, and this is a bulb that's corresponding to that switch. All right. Now the bulbs are either on or off, and we're going to call that the state of the bulb. So the bulb can be either in the state called on or in the state called off. So either this bulb is shining, it's on, or it's not shining, and we'll call that off. Now here's the thing. Somehow this mechanism has been wired together so that when you push on a button, it toggles the states of that bulb and its two neighbors. So let's take a for instance. When I flip on switch A here, when I hit switch A, when I push that button, if this bulb is currently on, it's going to go off. But it's also going to have the effect of toggling the two neighbors as well. So if this one's off, it will go on. And if this one is on, it will go off. So when I activate button B, it's affecting the bulb itself at A and its two neighbors. It's toggling their states. So ons are going to go to off and offs are going to go to on. All right. Now here's the problem. If bulbs A, C, and D are on and B and E are off, so if A, C, and D are on and B and E are off, devise a sequence of button pushes that will leave only bulb C on. So how would you describe a set of pushes, a set of buttons that you could push in some order that would change the system from on, off, on, off to off, off, on, off, off? So how could we do that? Now, one thing we're going to need to do as we work with this system of bulbs is we need to keep track of the state of the system at any given time. And to do that, we're going to introduce what's called a state vector. So we're going to let 1 denote an on, the bulb is on, and 0 denote off, the bulb is off. And we can use a vector, and we're going to arrange the components from A to E to record the state of the bulbs. So for instance, if bulbs B and E are on and all of the other bulbs are off, then we're going to record the state of the system as this vector here. So let's read this vector together, right? So this is position A. So bulb A is off, bulb B is on, C is off, D is off, and E is on. So this vector records the state of the system at this point in time, right? Which bulbs are on and which bulbs are off. Now, we can think of this, we can think of any of these state vectors as elements of the vector space Z sub 2 superscript 5. And if you remember how to read this, the superscript is telling me how many components my vector has. So there are going to be 5 components, 1 for each bulb. And the Z2 is telling me that these elements, the components themselves, are coming from Z2. So they're either going to be 0 or 1 accordingly. All right. Now, let's see how we can leverage the fact that this is Z2 to do some arithmetic to help us keep track of how these state vectors get updated as buttons are pushed. Now, as we continue to push buttons in this system, the state vectors are going to change. And what I want to try to show you is that we can think about the changing states of this system through vector addition. All right, so we will encode the action of pushing a button into a vector, which we're going to call the button vector. So button A is going to have a vector associated with it. Button B will have a vector associated with it. On down to button E will have a vector associated with it. And what we're going to see is that pushing a button is equivalent to vector addition in Z2.5. In other words, we'll be able to take the current state of the system. When I want to push button C, I'll be able to pull out the appropriate button vector, the button vector that's associated with button C, and by adding that button vector onto the current state of the system in the Z2 sense, I will update it and I will get the new state of the system. So pushing a button will be equivalent to doing vector addition on the state vector. So let me show you the button vectors that are associated with each of the 5 buttons. So here are the button vectors. So associated with button A, we have the vector with components 1, 1, 0, 0, 1. And what I want you to notice is that the 1s are in the positions that the push of button A affects. So remember, when we push button A, we'll have an effect in position A, position B, and position E. Those are the lamps or bulbs that are adjacent to bulb A. When we push button B, we'll have an effect on B, A, and C. So in each and every one of these button vectors, we'll see that the ones are in those positions, those bulbs are associated with those bulbs that can be affected by the push of that button. Okay, so the button vectors are in a sense easy to describe, they're easy to figure out. But let's take a look at an example so we can understand how this action works, or how this vector addition is going to work. So let S be the vector with components 0, 1, 0, 0, and 1. Let that be the current state of the bulbs. So what are we seeing? We're seeing that bulb B is on and bulb E is on, but A, C, and D are all off. And we want to know, what is the effect of pushing button B? Now, before we think about it in the vector sense, let's just use our common sense, right? Let's see what happens here. B is currently on, and its two neighbors are currently off. So when we hit button B, it's going to toggle this bulb. It's going to go from on to off, and the neighbors are going to go from off to on. And so the new state vector should be 1, 0, 1, 0, 1. Now let's see how we can have that same effect by adding the appropriate button vector to the current state vector. So our state vector here is listed. The button vector that's associated with button B is 1, 1, 1, 0, 0. And when we do the vector addition now in the Z2 sense, all the component addition is going to be in the Z2 sense. We're going to have the 0 and the 1 giving us a 1 in the first component, the 1 and the 1 giving us a 0 in the second component, the 0 and the 1 together giving me a 1 in the third component, the 0 and the 0 retaining a 0 in that fourth component, and finally the 1 and the 0 giving me a 1 in the fifth component. In other words, our updated state vector is exactly what we got when we just used our common sense. But we have this new way of thinking, right? We can update our state vectors by adding these button vectors. Let's look at a slightly more complex example. So imagine we have exactly the same starting state vector, 0, 1, 0, 0, 1. But now I want to push button B and then button D. So what I can do is take my state vector, my button vector B, and my button vector D, and now I can add, right? I can add in the Z2 sense and get the updated components, right? And I just have to add 0, 1, and 0 in Z2. That's 1. 1, 1, and 0 is 0. 0, 1, and 1 is 0. 0, 0, and 1 is 1. And 1, 0, and 1 is 0. So there's my new state vector. Bulb A is on, bulb D is on, and all the other bulbs are off. Now here's something interesting that we can learn by studying this example. We added these vectors in the order S plus B plus D because we imagined first pushing button B and then pushing button D. But we know that vector addition is commutative, so we're going to get the same result if we add them in the order S plus D plus B. In other words, we can switch the order of these two vectors without changing the result at all. And what that tells us is that at the level of button pushing, it doesn't matter if we push the buttons in the order B then D or D then B. The order in which the buttons are pushed apparently doesn't matter because that's what the vector addition is showing us. Let me show you how we can use this property that vector addition commutes to keep things simple. So let's imagine the following example. Suppose I have some initial state vector. This is the state of the system when we started, okay? And then I go through a mad sequence of button pushes. I hit A, and then E, and then B, and then A again, and then C, and then E, and then B, and then A, and then finally D. So I go through this mad sequence of button pushes. But now we stare at this and we know that this system, this set of additions is commutative. So what I can effectively do is take all of the A's, there are 3 of them, I can imagine doing them first. Then I can take the B's, and there are 2 of them, and I can imagine doing them next. Then I can take the C, and then I can take the D, and then finally the 2 E's. And I can imagine having the same effect by taking my initial starting vector, my initial state vector, hitting button A 3 times, then hitting button B twice, then hitting button C, then hitting button D, and then hitting button E twice. So even though the string came to me in this order, it's equivalent to carrying out these button pushes in this order. All right, now let me add one more element. This really simplifies things, all right? Anytime I add a state vector, anytime I add a button vector to itself, A plus A or B plus B or C plus C, it's always going to add to the 0 vector, right? Because the 1s line up perfectly and the 0s line up perfectly. Everywhere we add a 1 to itself in a component, it's going to add to 0. And everywhere where we add a 0 to itself in a component, it's going to add to 0. So effectively, when we see an odd number of hits on button A, here we see the 3A, that's equivalent to just hitting button A once. These 2 hits on button E are equivalent to not hitting button B at all. We've got the 1 hit on C, the 1 hit on D, and the 2 hits on E is equivalent to not hitting button E at all. It's like adding the 0 vector. So what I'm claiming is that even though we've got this mad sequence of button pushes that we did, it's equivalent to taking our starting state vector and hitting button A once, hitting button C once, and then hitting button D once. We don't have to touch buttons B or E, and we'll have exactly the same effect as this. All right, so this has been a fairly lengthy digression. Let's remember what the original problem was. We had our bulbs in this original configuration. We had bulb A was on, bulbs C and D are on, but B and E are off. So this reflects the original state of our system of bulbs. And the question was, could we bring it to this state where only bulb C is on and all the others are off? Can we do that through a sequence of button pushes? Now, what we've learned about these button pushes is that it never pays to push a button more than once. So either you're not going to push it or you're going to push it. So if you want to affect the change from this state to this state, you have to make a choice. Do I hit button A or not? That's equivalent to choosing this coefficient alpha equal to 0, not hitting button A, or 1, hitting button A. And you need to make a similar choice for every button. So what this boils down to is, can I solve this system of equations in alpha, beta, gamma, delta, and epsilon equaling elements of Z2? In other words, being equal to 0 or 1. All right, so this is equivalent to solving a system of equations in Z2. Now, let's go to the document camera and I'll show you how we can make one more adjustment to this system, and then we can do some row reduction to work out a solution to this problem. All right, welcome to the document camera. So here's the problem that's before us. We've got our button vectors, A, B, C, D, and E, and we have to choose, we have to make choices alpha, beta, gamma, delta, and epsilon. Those are going to be 0 or 1. And that's effectively saying, am I going to use button A or not? Am I going to use button B or not? On out to, am I going to use button E or not? To affect the change from this state to this state, I want to go from where bulb A, C, and D are on only to bulb C is on only through some sequence of button pushes. Now, this is going to be doing all of our work in Z2. We're basically going to be solving this problem in Z2, so we're going to be doing Z2 arithmetic all the way through. Now, that does make things pretty simple. On the other hand, it is a large system, so there's quite a few steps involved in the row reduction. All right, now, let's first of all clean this up a little bit. My unknowns are alpha, beta, gamma, delta, and epsilon. And I know that I want to have those unknowns on the left, and I want to have my column of constants on the right. So what I have to do is get this column vector from this side to this side. So I have to think of what could I add to this column to get rid of it on the left and put something else on the right. And since we're working in Z2, I can just add this vector to itself. So I can just add this vector again on this left-hand side. And this is because we're working in Z2. Okay, now these two vectors will add together to give me 0, because everywhere the 1's meet is a 0 and everywhere the 0's meet is a 0 in Z2 addition. And so this system will boil down to alpha A, beta B, gamma C, delta D epsilon E is equal to the column vector I get by adding these together. So the 0 and the 1 will meet to give me a 1. The 0 and the 0 give me a 0. The 1 and the 1 give me a 0. The 0 and the 1 give me a 1. And the 0 and the 0 give me a 0. So this is the system that I'm solving, right? Can I make some choices for alpha, beta, gamma, delta, and epsilon so that this vector sum is equal to this? All right, now, as an augmented system, this is going to form my column of constants. And now I have to take out these button vectors and write them as the successive columns of my augmented matrix. Now let's remember the button vector A made an effect on bulb A, B, and E, so that's where the ones are going to appear. Okay. Button vector B has an effect on B, A, and C. Okay, that's the effect of button B. Button C is going to affect B, C, and D. So we've got A, we've got B, we've got C. D is going to have an effect on the last three. And then finally, E is going to have an effect on A, because that's a neighbor. Not on B, not on C, but on D and E. So there's our augmented matrix. Now everything, remember, everything is being done in the Z2 sense. So all of our work in elimination is all being done in Z2 arithmetic. Now, I'm not going to show you all the steps, but I will show you a few steps just to remind you of what these row operations are going to look like in the Z2 sense, and that will help you get started. And I would encourage you, I'll show you what the finished matrix looks like, but this will encourage you to maybe try to fill in all of the missing steps. But I want to show you a couple of steps because there's, again, working in Z2 keeps things, makes things very interesting. Okay, so let's think about what we want to do. We're going to row reduce this now, all of our arithmetic being done in Z2. So we've got the leading one here in this position, which is fantastic. That's in row 1, but we need to get rid of the ones that sit below it in row 2 and row 5. So here's what our first set of row operations is going to look like. I'm going to take 1 times row 1 and add it onto row 2. And I'm going to take 1 times row 1 and I'm going to add it on to row 5. And that's going to have the effect of eliminating the ones here and here. Okay, let's think about what's not changing. Row 1 is not changing, so let's fill that one in. Okay, row 2 is changing, so we won't fill that one in yet. Row 3 is not changing, so let's get that one in. Okay, row 4 is not changing. But row 5 and row 2 are changing. So let's get those changes. And we're getting them simply by adding row 1 onto them. So let's get the change in row 2. So when the 1 adds onto the 1, that's a 0. When this 1 adds onto that one, I get a 0. When the 0 adds onto the 1, I get a 1. 0 plus 0 is 0. 1 plus 0 is 1. And 1 plus 0 is 1. So there's the new row 2. Now, let's take a look at the effect in row 5. Remember, I'm adding row 1 onto row 5, so I'm now working with these two rows. So let's make sure we get the addition done correctly. When this one adds onto that one, I'm going to get a 0. We wanted that. When this top one adds onto the bottom 0, I'm going to get a 1. The two zeros add to 0. The 0 and the 1 add to 1. And the 1 and the 1 add to 0. In the constant column, I'm going to have the 1 and the 0 adding to 1. So that's the state of our augmented matrix after taking this leading 1 and eliminating everything in its column. And now you see we're in an unfortunate position because we would like to have a leading 1 in this position in the next row. We're going to need 1 because we've got these elements here, but our next 1 is way over there. So what I'm going to do now is do a row switch. I'm going to switch rows 2 and 3, and that'll bring that leading 1, this leading 1, up into this position. So here's a switch. All right, so let's get row 1 written. Now I'm going to take the old row 3 and promote that to row 2. Make sure I've got that right. 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0. Good. Always helps to double and triple check here. We're going to take the old row 2 becomes the new row 3. So 0, 0, 1, 1, 1. And the last 2 rows are unphased, unchanged. Okay, good. Now, I've got a leading 1 in the second row, and I want to use it to eliminate the things, the non-zero elements in its column. So I have to do another pair of row operations. Now I'm using row 2 to affect row 1, and I'm using row 2 to affect row 5. So my next operations are going to be take 1 times, got to get this right, take 1 times row 2 and add that onto row 1, and take 1 times row 2 and add it on to row 5. Now let me get row 2 in place. That's not changing. Okay. Now what I'm going to do is concentrate on these top 2. I'm taking row 2 and adding it up onto row 1. So that 0 is going to go up and meet that 1. That's still a 1. The 1 and the 1 will give me a 0. That was the whole point of the operation. This 1's going to go up to give me a 1. This 1 will go up to give me a 1. The 0 will go up and give me a 1. This 0 will go up and add on and give me a 1. So there's the new, in effect, the new row 1. Okay? Now, the next couple of rows are not being affected. 3 and 4 go in as they are. So let's get 3 in. Let's get 4 in place. Make sure I did that right. Is that 3? Okay, 4. And now I have to make a change in row 5 according to this recipe. So bring row 1 down and add on to it. So, excuse me, bring row 2 down and add on to it. So 0 and 0 are 0. The 2 1s meet to give me a 0. I get a 1. I get a 0. I get a 0. And I get a 1. All right, so that's the state of our augmented system at this point. Now, there are 3 more steps that we would have to do to bring us to the final form. I will cut to the chase here. So I'll just say there are a few more row steps that we would have to take. I wanted to show you the first few just to kind of get you started. And I especially wanted to show you the row switch because that's a rare thing that we do, but it is something that shows up every now and then. Here's the final state of our system. This row reduces very nicely. Each and every row has a leading 1. Beautiful. And the column looks like this. Okay? Now remember, our variables are alpha, beta, gamma, delta, and epsilon. And what this is telling us is that alpha is equal to 0. Don't use button A. Beta is equal to 1. Use button B. Gamma is equal to 1, so we should use button C. Delta is equal to 0. Don't use button D. And epsilon is equal to 0. Don't use button E. All right, so our recipe is going to be the recipe that takes us from this initial state to this state is to do one button B and one button gamma. All right? All right, well, let's give it a try and see if this actually works. This was our initial state vector. We're supposed to use 1b. That's what the beta equals 1 is telling us, 1b vector. And if you remember, vector b looks like this. B affects A and C. And we're supposed to use 1 gamma, right? Gamma is equal to 1, so 1c. And that's what a C vector looks like, right? It affects positions C, B, and D. Let's see what the final state is according to this, right? So the 1, and the 0 are going to add up to 0. The 0, the 1, and the 1 are going to add up to 0. The 1, and the 1 will add up to 1. 1, 0, 1 adds up to 0, and 0, 0, 0 adds up to 0. So that brings us from our initial state to our final state by doing 2 button pushes. Now you're probably thinking to yourself, you know what, in the time it took us to set this problem up, do all the row steps, and find this solution, which is as trivial as pushing 2 buttons, you think you might have been able to find that just by poking around. And it's probably true because this is not a big system. But you have to imagine if the system was big, if this was a big system, right? And there were lots of choices of moves, right? The number of possible configurations of moves grows exponentially fast, right? So this could become a very hard problem once the system achieved any kind of size. So what you have to be aware of is that this is a technique that's extendable. We can extend this technique to much larger systems, and we can bring some computers to bear on doing some of this grunt work, some of this row reduction for us. And so really the charming thing about this is that we could scale this problem up considerably, and we could still use this technique to find a fairly fast and efficient solution with the aid of a computer and not have to check the large number of possible arrays of button pushes that we would need to take us from some initial state vector to a final state vector. So this is really something that would be very beneficial if the size of the system got considerably larger. So it's nice to work it out in a case where the system is small, but the real benefit of this kind of technique would be on systems that are considerably larger. Okay, so I hope that was interesting to you. And that brings an end to our adventures in applications. So that ends our discussion of section 2.4. So the next time I see you in a video lecture, we will be into chapter 3, section 1. So join me for that. I'll see you later. Until then, take care. Bye-bye.